All right, welcome back. So now let's get into the process for actually graphing the cosecant, the secant, and the cotangent function. So we're going to start with the cosecant and the secant. And the process that I really like to be able to do for this is, again, still like identify our transformations, right? But to understand the characteristics of these graphs, I think a lot of times it's easier to graph the reciprocal. So what that means is I'm going to, for each of these, I'm going to graph the reciprocal function first, so therefore I can better understand and better identify the characteristics such as the domain, the range, as well as the, just the domain and the range actually. So let's go ahead and first just kind of identify the transformations here. So in this case, we're going to have a vertical stretch of 2, and we are going to reflect the x-axis. Reflect the y-axis. Okay. And then what I'm going to do first is rather than figure out graphing the cosecant graph, I'm going to graph, well, actually, let's go and identify, actually, we don't have any phase shifts, right? Because we're not shifting the graph left or right, and we are not shifting the graph up or down. So what I'm going to do is I'm going to first graph the reciprocal function. So I'm going to graph y equals 2 sine of negative x. Okay. Now, again, if this graph is going to be reflected, if you think about sine being reflected about the y-axis, like if you just think about this real quick, that's not what I wanted it to do. And of course it decent. Come on. Can't draw a straight line. Okay. There you go. There's your graph. Okay. So here's the sine graph, right? And it looks something like this. If obviously you flip this around, if you flip this about the y-axis, right, what I want you to see is this graph, it's kind of the same as being reflected about the x-axis, right? Because now the graph is going to be like this, right? So if you flip it about the y-axis, it's actually going to go in the opposite direction. We see also that the amplitude of sine is going to be the amplitude of sine is going to be 2. That means the graph is going to go up to 2 and down to negative 2. So there's no shifts to the left and to the right. So we know that the graph is going to end at 2 pi and it's going to cross at pi. Okay, so I'm going to have go down, go up. Oops, sorry about that. I forgot. I'm like, I don't want to confuse you. That's going to be 1 and 2, negative 1 and 2. Okay, so we know that it's going to go down to 2 and then go up to 2 here. So I want to use the And again, you could obviously continue this if you wanted to go and find the x scale. You could go in the negative direction and the positive direction. I just mainly want my students to be able to understand where the graph is, what it looks like. We know that wherever the graph crosses the x-axis, that there's going to be asymptotes. So there's asymptote here, there's an asymptote there, and there's a vertical asymptote here. And then the graph is, again, just the mirrored image from here. Okay. So that's just going to be one period of my cosecant graph. But it's important about understanding this because obviously we know that this stretch has impacted my range. So again, one of the things we looked at, and if you remember section 1 of this course, was we talked about the range from a graph. And that's why I kind of like to do it this way, is you can see, well, if we're looking at the range of the graph, it's rather kind of simple. It's like how low is the graph going to how high is it going? Well, you can see here, the graph is going all the way down to negative infinity, and then it goes all the way up to negative 2. Now, again, it's included at negative 2, so we're going to use a bracket. And then there's nothing that's going on from negative 2 all the way until we get back to 2. So then we can go from union from 2 to infinity, right? So we can connect from negative infinity to 2 and then 2 to infinity. Again, 2 is going to be included. Now the domain is going to be all the values that are not included for your asymptotes. So let's go and take a look at where the asymptotes occur. Now again, the period is 2 pi, right? And that didn't change. We didn't stretch or compress the horizontally. So you can see we have an asymptote here at pi. So I can say x equals pi. And then it looks like the distance to each and every asymptote is going to be pi n. So plus pi n. Now what if we can simplify this? Do we really need to add a pi? Could we just go start from 0 and say pi n? And yeah, so you could actually simplify this by writing it as pi n. So my domain is going to be all values of x such that x cannot equal pi n. Okay, and that would be your domain in that case. You could also write all real numbers many different ways. I'm just kind of giving you some different variations. All right, so for the secant graph, again, going to do the same thing. This one's reflecting about the y-axis, so I'll just say reflect the y-axis. And then now we're going to have a phase shift. So I'm actually going to do this I should probably just write the period. Period is 2 pi. So now we're just going to go left pi halves. Okay, now this is the trigonometry, verbiage. What I want to do is I just want, again, main thing we want to look at is the phase shift and the period. So in this case, the period, I do not have a b, so my period is 2 pi. And we can say the phase shift is going to equal, pi halves left. Okay, or positive pi halves. Usually we can just see if it's positive, then it's going to be going to the, that's a negative pi halves. So we're going to say the phase shift. We could say pi halves left, or you could just say a negative pi halves. All right, so now let's go ahead and graph the secant graph. Again, we notice that the graph is going to be reflected about the y-axis. The x-axis, and that's very important because if you look at the graph for cosine, right, it looks like this. So if you reflect that about the y-axis, it's going to not look like that, right? So again, just make sure you understand that. So we have that reflection, and then the graph is being shifted pi halves to the left. So that's going to be important because now what we're going to want to do is find our new kind of starting point and end points. So I'll just say starting point is going to be x plus pi halves equals 0. And then my end point is going to be x plus pi halves equals 2 pi. So therefore, x equals negative pi halves. And then over here, we can rewrite 2 pi. So actually, let me actually do this over here. Actually, I'll just put that over there. That's fine. Here, actually, you know what I'll do? Let me kind of run out of space. I don't have a lot of room for this. Let me put this down here. All right, so therefore x is going to equal, this would be 4 pi over 2 minus pi halves. And that x equals 3 pi over 2. Okay, so that's where we're going to start. So I'm just going to say, all right, so here's going to be 0. Okay, and I just bring this down even more. Jeez. Keeps on don't have any room. All right, so we'll say, all right, here's where we're going to start. So this is going to be negative pi halves. And then we're going to go to 3 pi halves. And again, I'm just scratching the graph, guys. Okay, so if you look at your x scale, that would be 2 pi divided by 4. So that would be pi over pi halves. So therefore, we'd have another corresponding point here. We'd have another corresponding at pi halves, at pi, and at pi, right? So 1, 2, 3. So 0, pi halves, pi, and 3 pi halves. Yeah, okay. So again, the cosine graph is going to go up to 1 and down to negative 1, right? But again, remember it was reflected. Don't forget that. So this graph is going to look something like this. Okay, but again, that is the cosine graph, right? We're not graphing the cosine graph. We are graphing the secant graph. So wherever there is an x-intercept, that's going to be our new vertical asymptotes. And you know what I need to do? I'm just going to compress this. Whoa. Why are you being like this? Okay. So then this graph is going to be open like that. You can see it's approaching. All right. So I'm actually going to do, don't give me any room for this. All right. Then the last thing we need to do is identify the domain and the range. So the domain, you can see that there's not a vertical asymptote that got moved. You can see that the domain looks like this is going to cross, looks like at pi, right? Now again, a couple things that you can be able to identify with this is you can just go ahead and same thing. If you look at this graph, it looks like, yeah, it's going to be crossing at 0 and at pi. So in this case, the asymptote, it looks like it's going to be at x equals pi, again, plus pi n. So x equals pi n. So my range, it looks like it goes down to -1 up to 1. So my range is going to be from negative infinity to -1 union 1 to infinity. My domain is going to be the opposite of this, the opposite of my asymptotes. So that's going to be all values of x such that x cannot equal pi n. All right. I think it's really important that we have, I can't believe that. Why would you not? What is going on? That is really weird. Okay. Let's go ahead and do the start and the end. So again, we have this x plus pi halves equals 0, and x plus pi halves equals 2 pi. So x equals negative pi halves, and x equals 3 pi over 2. Okay, so that's going to be all the way in from there. I have no idea why that is getting me to there. All right, let's go ahead and work in the cosecant. So this one, you can see that the 2/3 is going to be, 2/3 is less than 1. So therefore, that is going to be a horizontal stretch of 2/3. And then we're going to shift the graph up 1. All right, now the period is going to change, right? Because that's our b. So we'll have a 2 pi divided by 2/3, multiply by the reciprocal. That's going to equal a 3 pi, right? So you multiply by 3 over 2. I guess I'll just show my work. So multiply by 3 over 2, 3 over 2, 2's divide out. You're just going to be left with a 3 pi. There is no phase shift, so we don't need to worry about the graph shifting left or right. However, whenever we have a phase shift or we have a B, a compression or stretch, that's going to change our start and our end. So the start's not going to change, but but the end is going to. So let's go ahead and figure out the new start. That's going to be 2x divided by 3 equals 0. And our end, so that's just going to be x equals 0. And then our end is going to be a 2x over 3 equals 2 pi, right? Now, if you multiply by 3, that's going to give you 6 pi. And then divide by 2, that will give you 3 pi. Okay, so that's very important because it doesn't matter even if I'm graphing sine, I'm going to go to 3 pi, right? It's going to go from 0 to 3 pi. Now, the x scale is going to be a little weird here, and that's okay. But again, like I don't want to spend too much time. I just want you to understand like where the period is, where the start and the end, and then just kind of go from there. So so let's go and graph the sine graph here. So the sine graph. All right, so the sine graph is going to go from, we have 0 to 3 pi. Okay, now the graph goes up to 1 and -1, right? The amplitude of sine is going to be from 1 to 1, but then the graph gets shifted up 1, right? So it's this graph being shifted up 1. So now it's going to go up to 2. So therefore, sometimes what I like to do is just draw the x-axis kind of like as a dashed line. So therefore, I can just remember where things are going to be. So this would be 3 pi halves, which is like 1.5. Okay, if you just kind of think about the marks there. So we're going to have here, we're going to want to dash this line. So yeah, sometimes when you're doing those vertical stretches, it's helpful to be able to see where those graphs, where those would be. Now, the other thing that's very important is to look at where those asymptotes are going to be, right? Because remember, like when we're looking at these x-intercepts are going to be from the reciprocal function. So it doesn't matter if we shifted up 1, we're still going to be looking at where, if without the vertical shift, where this function was going to be equal to 0. Because again, like when you plug in your angle, right, you can't have your function to be equal to 0. So our asymptotes are still going to remain at the intercepts. Okay, so even if the graph gets shifted up or down, that's still going to be where those original x-intercepts would be, because the shifting up or down is just going to be moving. It's not going to impact, that's not going to change the new x-intercepts, okay? So a lot of times, I mentioned that it was easier to think about them like when they're going to be equal to 0, but that's only before you do the vertical shift left and right, all right? So now my graph is going to go from here and then we just do the mirrored image. Okay. So now we can go and take a look at the domain and range. So the domain, or let's go and take a look at the asymptote here. Run out of room. So my asymptote is going to be x equals, looks like we're at 3 pi halves, and then the distance from each asymptote looks like it's another 3 pi halves, right? 3 pi halves plus another 3 pi halves gives you 3 pi. So that's going to be x equals a 3 pi halves plus 3 pi halves n, which is just equal to 3 pi halves n. Okay, so now what we can do from here is we can identify the range as well as the domain. So my domain, running out of space here. So my domain is going to be all the values of x such that x cannot equal 3 pi halves n. And the range is going to be going down from negative infinity up to 0, and then from 2 to infinity. So that would be from negative infinity to 0, union 0 to infinity. All right, next one in the secant graph. So now this one's kind of nice because really there's nothing going on left or right, right? All we know that there is this, which is a vertical stretch of 3 halves. So in this case, I'm just going to graph the period is going to be 2 pi. Okay, so I'm just going to graph the cosine graph here. And we know it's going to go up to, again, so that would be 2, negative 2, right? Okay, so there's going to be 3 halves, is halfway between 1 and 2, or negative 1 and negative 2. And then we're going to go up to 2 pi. Hopefully you recognize that that point is going to be pi. Cosine graph is going to cross from there. Oops, let's do this dashed. There you go. And there you go. Okay, and again, if you know that's pi halves where that would occur. But anyways, we're looking at there, and we're looking at there. But actually, never mind. It's actually important for you to understand that that's where that asymptote occurs, because that's what we're going to be looking for our domain. That's where the this graph is going to equal to 0. So now I can just go ahead and graph this here. All right, so let's go and look at the range. I think is probably the easiest one to start off with. This goes down to negative infinity to negative 2, union 2 to infinity. The asymptotes occur, like where is this, right? Well, again, this is going to be halfway. If you look at the x scale, if you take the period, divide it by 4, right? So 2 pi divided by 4, that's every pi halves, right? So 2 pi over 4 is pi halves. So pi halves plus 2 pi halves, 3 pi halves, 4 pi halves. So we can say this is going to be x equals pi halves plus pi n. Because here's pi halves, here's 3 pi halves. You can see the distance there is pi, right? So therefore the domain is going to be all numbers, all x's, sorry about that, such that x cannot equal pi halves plus pi n. There you go. All right, so now let's go and move into the cotangent. And the nice thing about cotangent is it's very similar to like tangent. We don't really need to now write the reciprocal. We just need to kind of know what the parent function is and then apply the characteristics. But please remember when you're dealing with cotangent to remember that the period is pi. There's no amplitude, right? Notice I didn't do any amplitude here, but I did use the idea of amplitude to sketch the graph, right? There are asymptotes. The asymptotes begin at 0 and at pi, and then they repeat every pi n from there. Now, in this example, we don't need to worry about graphing the reciprocal cotangent. We're just going to graph this function. I will go ahead and rewrite this, though, as a, hopefully you guys can follow me with this. We can rewrite this as a, let's see, a cotangent of negative x plus pi halves, which can be rewritten as a cotangent, not cosine, don't do that. A cotangent of a negative times x minus pi halves. All right, so we don't have a phase shift. I'm sorry, we don't have a period change, but we do have a phase shift of pi halves. And if you could be more descriptive, you say pi halves to the right. And then we have a reflection. So we'd say reflect the y-axis. Okay, now for this example, what I'm going to do is I'm going to show you the parent graph, and then we're going to kind of talk about what the graph would look like for the new graph. So remember, here is the parent graph. Here's pi halves. Asymptote here, asymptote there. The graph looks something like that. All right. So if we reflect this about the y-axis, I want you to see that this graph is going to change, right? So now this graph is actually going to look more like the tangent graph, where it's going to be increasing rather than decreasing. All right, so when I sketch my graph, I'm going to make it an increasing graph. And then the graph is being shifted pi halves to the right. Now, you could do the start and end if you wanted to, but I want you to see if you flip this graph and shift it pi halves to the right, like here's pi halves, right? Because we know that the period of the graph is, from 0 to pi. And so therefore the intercept's halfway in between. Well, the interesting thing about this is if I now shift this over pi halves, then it's going to be at the x-intercept. And therefore, if you flip this about the y-axis, the asymptotes are not going to change. But when I shift the asymptotes over, now they are going to change. Instead of being at 0, now they're going to be at a negative pi halves. And hopefully, you maybe start seeing the connections, what's happening here. I'm actually drawing the tangent graph. It's actually a cool kind of thing. So yeah, when you apply the transformations here, it's a really bad tangent graph, but hopefully you understand. But yeah, when you reflect about the y-axis and shift the graph pi halves units to the right, not the left, but if you shift it to the left, you get the tangent graph. But this did not ask us to shift it to the left, did it? This said shift it to the right. So we're going to have to be careful trying to go too fast. And let's reverse back. We know that the shift area is going right. So the graph looks like that. We reflect about the y-axis, so now it's going to look like this. But now we're going to shift it over pi halves to the right. So if we shift it pi halves to the right, you actually still would provide the exact same graph. But as far as the initial period looks, I don't want to confuse you with that. So now my x-intercept, it was at pi halves. Now it's going to be at pi. So pi halves will have that. And then this would be at 3 pi halves, would be this asymptote. Okay, so the graph is going to look like that. And again, if you repeat it, then you would see that graph does exist. I didn't want you to feel like, why are you going to the left when you're supposed to go to the right, right? So here is the parent graph, right? And then again, here is the graph just being repeated. And again, you could repeat it in both directions. So let's go and take a look at the domain. You can see the domain is the same as tangent, right? It occurs at pi halves plus every pi n. So before we talk about domain, we'll just say asymptotes. That's going to be x equals pi halves plus pi n. Sorry about that. The range is nice because that's going to be negative infinity to infinity. The domain is going to be all values of x such that x cannot equal pi halves plus pi n. All right, on to the last example is going to be, again, the cotangent. Now, this is going to have a b, so that's going to be a period change. So in this case, the period was still pi, right? Because negative pi divided by absolute value of negative 1 is still just going to be pi. Here, we got to identify, since b is larger than 1, that's going to be a horizontal compression of 3 halves. So when we're looking at this, that's going to be a period change. So if we take our period is going to be pi divided by 3 halves, multiplied by the reciprocal. That equals 2 pi over 3. All right, so that means, again, if you remember, the graph starts at 0 and then goes to pi. So if I have a period change here, this one's actually pretty nice here. Since I don't have a phase shift like I did over here, I can just draw my asymptote here at 0. And then my new period is going to be, if you just think about this, like when you set it equal to pi, your new asymptote is just going to be at 2 pi over 3. Okay. Now, if you want to find where this x-intercept would be, again, you can just take 2 pi over 3 and then divide it by 2. Multiply by the reciprocal, which equals pi over 3. Now the graph is not being reflected, so it's going to take the same shape as the original parent graph of cotangent. So it's going to be down and increasing. Okay. So our asymptote is going to occur at x equals we can see that it occurs at this 3 pi halves and then plus the period 2 pi over 3. So we could say like 2 pi over 3 plus 2 pi over 3n. Well, that's kind of redundant. We don't need to keep on adding that. If you kind of remember, we did that for the pi and the pi n. So we're just going to write x equals a 2 pi over 3n. The range is easy. That's negative infinity to infinity. And the domain, guys, is just going to be all values of x such that x cannot equal 2 pi over 3n. So there you go, ladies and gentlemen. That is how you graph the cotangent function as well as our reciprocal functions, the cosecant and the secant. I hope this was helpful for you. I know sometimes they can be a little bit, overwhelming looking at all the different parts, but I really think if you can identify the phase shift, the amplitude, and know what the graph looks like of the reciprocal function, you can better answer the questions for the asymptotes, the domain, and the range. So there you go, ladies and gentlemen. Go ahead and give it some practice here on the quick quiz, and I'll see you guys in the next section. Cheers.